Pull strength of CMOS system, effective size of MOSFETs when connected in first series and second is parallel, and third is calculating on-chip area of a CMOS system. So the purpose of discussing topic number 3 is to justify why, when a choice is given to a VLSI fabrication engineer between NAND gate and NOR gate as universal gates, why he chooses a NAND gate, that we will try to justify today. So to explain pull strength of CMOS system, we will again go back to the simplest and smallest possible CMOS system, that is a CMOS inverter. So always remember that whenever a question is asked that which is the simplest and smallest CMOS system, the answer is CMOS inverter, because it contains one PMOS and one NMOS. So pull strength of CMOS system. Consider the simplest and smallest CMOS system, that is CMOS inverter. As shown below. So the transistor level schematic of CMOS inverter looks like this. The power rails, we out. Okay, and the level at which we are discussing CMOS inverter now, it would be incomplete if I do not mention the size of PMOS and NMOS. So here we know the size of PMOS is given as small p equal to width of PMOS upon width of NMOS, which must be equal to 2.5 times n, and we know that small n is size of NMOS, Wn by Ln, which we told that it should be 1.5. Okay, so the size of PMOS comes out to be 3.75, right? And we already justified mathematically, and also we have proved it using simulation, that in a CMOS inverter circuit, only when the size of NMOS n is equal to 1.5, the size of PMOS p is 2 times n equal to 3.75, then the result of these dimensions are that we get T rise equal to T fall. Okay, so in essence I can tell that, okay, now so before we go ahead, now we will define what is called as a pull strength of a CMOS system. So in the beginning of the unit only we had discussed that for V out equal to logic 1, the output node must be connected to plus VDD. And for V out equal to logic 0, the output node should be connected to minus VSS. And we also told that if this connection happens through a PMOS device, then we get V out equal to strong 1. Similarly, if this connectivity between output node and ground happens through NMOS, then we get V out equal to strong 0. Already discussed this thing. So the size of the device through which the output node gets connected to VDD gets the name pull-up strength. So we can first define what is pull strength, and then we will define what is pull-up strength and pull-down strength. So we can define pull strength. Pull strength is in terms of the size of MOS device through which output node gets connected to plus VDD or minus VSS. So I repeat, pull strength is defined in terms of the size of MOS device through which output gets connected to plus VDD or minus VSS. That is why the size of the MOS device through which output node gets connected to VDD, it is called as pull-up strength. Similarly, the size of MOS device through which output node gets connected to minus VSS now gets the name pull down strength. Okay, and we see here that in the CMOS inverter, the pull-up network consists of one PMOS device, while pull-down network consists of one NMOS device, right? So in this circuit, in order to have equal rise and fall times, in this circuit to have equal rise and fall times, the size of the PMOS should be equal to P, that is 3.75, and the size of NMOS should be small n, that is 1.5. Okay, so we say that in the simplest and the smallest possible CMOS system, we can get equal rise and fall times if the pull-up strength is equal to small p, pull-down strength is equal to small n, whereas n is equal to 1.5 and p is 2.5 times 1.5, right? So we can write here now that thus to achieve T rise equal to T fall in CMOS inverter, the pull-up strength should be equal to small p and pull-down strength should be equal to small n, where p is 2.5 times n and n is equal to 1.5. Okay, and we can say that the relative size is equal to 2.5. So we can extend these conclusions for CMOS inverter to a generic CMOS system. So all of us know that whatever are applicable to CMOS inverter, they can be extended to larger and more complex CMOS systems. So we again come back to the generic block diagram of a CMOS system, which we discussed before, and we can put down the values of PUS and PDS here. So a generic CMOS system has VDD and VSS rails, and here I have my pull-up network, a mirror image of pull-up network. I have pull-down network, and the intersection between pull-up network and pull-down network is my output Y, and I know that whatever inputs I give to the pull-up network must also be given to pull-down network. And here in this system, to have equal rise and fall times, I must have the pull-up strength of the entire pulled up network should be equal to P, and the pull-down strength of the pull-down network should be equal to N. Is it okay? So now you know that pull-up network can contain all PMOSs in series or all PMOSs in parallel or a series parallel combination between PMOS devices. Similarly, the pull-down network can contain a series connection between NMOSs, a parallel connection between NMOS devices, or a parallel series connection between NMOS devices. Right. So it was very easy to find out what is the pull-up strength and pull-down strength in a CMOS inverter to get T rise equal to T fall, because the pull-up network contain only one PMOS and pull-down contain one NMOS. But when systems become larger, like NAND gate, we have two PMOSs in parallel and two NMOSs in series. In a NOR gate, we have two PMOSs in series and two NMOSs in parallel. And similarly, if you want to make the transistor level schematic of a 4-input NAND gate, then it will be 4 PMOSs in parallel and 4 NMOSs in series. So that is why we have to learn how to make sure that in the pull-up network, every path which can be taken from the output node to VDD must have a pull-up strength of P. Similarly, every possible path between the output node Y and minus VSS should have a pull-down strength N. That is why we refine our definitions again, that what is pull-up strength. So because there can be multiple paths between Y and plus VDD and multiple paths between Y and ground. That is why every possible path in the pull up and every possible path in pull down should have the pull up strength equal to P and N. So the last and the most refined definition of pull up strength and pull down strength can be put like this. So we can say that since there can be multiple paths between Y and plus VDD and between Y and minus VSS, the pull-up strength of each between Y and plus VDD should be equal to P, and the pull down strength of each path between output and minus VSS should be equal to N. This is the conclusion. Okay. Yeah. In order to ensure T rise equal to T fall. Now, almost all batches of BE8, I have taught how to make the layout for a NAND gate and a AND gate. So there in the layouts, we only focused on checking whether the functionalities of NAND and AND have been achieved. But we never ever focused on what are the values of rise time and fall time. And if we simulate and if we check it, definitely you will not get T rise equal to T fall. In fact, I was surprised to see that that in the NAND gates layout, I am getting rise time almost 12 times that of fall time. In a CMOS inverter, the rise time was 3 picoseconds and fall time was 1 picosecond. So T rise was only 3 times that of T fall. But when I simulated the layout for NAND and AND gate, at that time I got a multiplication factor of almost 10 to 12. So if we use today's conclusions in order to redesign the constituent MOSFETs of NAND and AND, I'm sure we will get comparable rise and fall time. That is what is the aim of discussion today. Now, we have already told that why can there be multiple paths between Y and VDD and Y and VSS? Because it is possible there may be series parallel and series parallel connections in both pull up and pull down network. That is why the next relevant topic is here, that is effective size of MOSFETs when connected in series and parallel. Okay. So effective size of MOSFETs when connected in series. Okay. Consider M number of NMOS devices connect series. Okay. So consider M number of NMOS devices connected in series as shown. So here we are going to draw the lower half of the CMOS network. So wherein we have the pull-up network coming from above, and then we have my output node Y. There are M number of NMOS devices which are connected in series. Okay. And then we have the last NMOS device here. So we have minus VSS and we have all NMOS devices connected in series. Let us also give them names as usual. So this is N1, N2, N3, and here we have the last device NM. Okay. Now let us also tell that their sizes are as follows. So the size of N1 is W1 by L1. The size of second NMOS is W2 by L2. That of third is W3 by L3. Similarly, the size of last NMOS device is WM by LM. Okay. Now another assumption which we do is that when these MOSFETs are in on condition, that is in saturation, they are offering an on-state resistance R. Okay. Now be the on-state resistance of each MOSFET. Okay. That means what we have to replace we have to replace each MOSFET with a resistance. Okay, so I replace N1 with R1. I replace N2 with R2. I replace N3 with R3. Similarly, I replace the last MOSFET with RM. Okay, so N1 is replaced with R1, R2, R3 and RM. Okay, now we know since years that whenever resistors are connected in series, the equivalent resistance is the summation of individual values. That is the same concept I am going to apply here. So now what is the effective resistance of m number of NMOS devices connected in series when they are in on condition? So it is like this. Okay, Y here, and we have one single resistance representing the series connection like this, minus VSS. Let me name this equivalent resistance as R equivalent. Okay, going ahead now, it's very clear that R equivalent is equal to R1 plus R2 plus R3 plus Rm. Now, another important fact which we had discussed before is that there is a mathematical model available for the onset resistance of a MOSFET, and that resistance is inversely proportional to W by L ratio. Okay, so also R on is equal to 1 upon K dash into W by L into VGS minus VT. In other words, the onset resistance of MOSFET is inversely proportional to W by L. Okay, so we have equation number 1 here, we have equation number 2 here. So we can write this term in equation number 2's RHS, replacing R1, R2, R3 up to Rm. Okay, so if R on or R is equal to 1 over K dash into W by L into VGS minus VT, neglecting body effect, what we can write is this. I can write down 1 upon K dash into equivalent W by L ratio into VGS minus VT is now equal to 1 is equal to 1 upon K dash into W1 by L1 into VGS minus VT plus 1 over K dash into W2 by L2 into VGS minus VT up to the last MOSFET 1 upon K dash into Wn by Lm into VGS minus VT. I have already told that we are neglecting the presence of body effect here. That is why we can clearly write it like this, that W by L equivalent of the series connection of MOSFET devices is 1 over 1 upon W1 by L1 plus 1 upon W2 by L2 plus 1 upon W3 by L3 up to 1 upon Wm by Lm. So this is equation number 3, which tells us that the equivalent W by L ratio of a series connection of m number of NMOS devices is equal to the reciprocal of the summation of the individual reciprocals of W by L ratios. Okay, and most important thing is this, that now you see here that we have considered a series connection between NMOS devices. That means this forms the pull down network. That means what? The W by L ratio of this series connection should be same as the W by L ratio of CMOS inverter. Okay, and the W by L ratio of CMOS inverter to have rise time equal to fall time is equal to N. That means even if we connect M number of NMOS devices in series in pull down network, the equivalent or the effective W by L ratio of this series combination should be equal to N, small n. Okay, that is why I write a comment here that W by L equivalent should be equal to N. Okay, so we say that the W by L ratio of series combination should be equal to N. So I say that the W by L equivalent of series connection of NMOS should be equal to N. Similarly, I can tell that instead of NMOS is connected in series, if I would have connected M number of PMOS devices in series in pull-up network, then it would be equal to P. W by L equivalent of series connection of PMOS device should be equal to P. Okay, so now we have equation number 3 shows what is the equivalent W by L ratio if MOSFETs are connected in series. Now we go to what is the effective W by L ratio if they are connected in parallel. So parallel connection between M and MOS devices. So again we have the pull-up network coming, output node Y, and here I have M number of devices connected in parallel. NMOS, 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 and the mth NMOS, and all of them are connected in parallel. N1, N2, N3, NM. So as per our previous convention, I replace every NMOS with a resistor R1, R2, R3 up to Rm. R1, R2, R3, Rm. And then we are interested to know what is R equivalent of this combination. We have a single resistor. We name this as R equivalent. So from network theory, we know that R equivalent is given as 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 plus 1 upon Rm, and using equation number 2 we can write it as K dash W by L equivalent into VGS minus VT is equal to K dash into W1 by L1 VGS minus VT to K dash so we can say in a parallel connection the equivalent W by L ratio is nothing but it is a summation of the individual W by L ratios. Yeah. So now we again go back to the series connection and we consider that what should be the sizes of individual NMOS devices if two NMOSs are connected in series. Okay, so it's very simple. Consider two NMOS devices connected in series. So instead of M devices, we put M equal to 2. Okay. Now you have to be very attentive. Okay. So now I have my device N1. Maybe I'll write it here. And the second device is N2. Okay. Now, if we want this series connection between two NMOSs to have the same fall time as that of CMOS inverter, so what I should do is that I have to see that if this circuit was a CMOS inverter, then I know that the size of this NMOS should have been N. So here the effective pull down strength of this series combination has to be equal to N. That means what? My W by L equivalent of the series connection should be equal to N. Okay. So again I repeat that so that the series connection between two NMOS devices in the circuit should have the same fall time as the fall time of a CMOS inverter, because in CMOS inverter the pull down strength is equal to small n. That is why the effective W by L ratio of the series connection should also be equal to n. Now for example I assume now what I do, I assume something. Says for example if I use n1 with size n and if I use n2 with size n, let me see what is the equivalent W by L ratio. So from equation number 3 what I can do is I can try to find out what is the effective W by L ratio. So we know that W by L equivalent of series connection is equal to 1 upon W1 by L1 plus 1 upon W2 by L2. Okay, so understand one thing, that this is nothing but W1 by L1 and this is W2 by L2. So I will substitute the values here. So I get equal to 1 upon n plus 1 upon n, which comes out to be n by 2. We do not want n by 2. The expected value of W by L equivalent is equal to n, not n by 2. So what I do is that if I use the sizes as 2n and 2n, if I say it is 2n and 2n, naturally my goal is achieved. So in this case, my renewed calculation would be equal to 1 upon 2n plus 1 upon 2n, which is equal to n. This is what we wanted. So what is the conclusion? That if I connect two NMOSs in series, then the individual sizes should be 2n and 2n. If I connect three NMOSs in series, I should have the sizes 3n, 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 so that the equivalent W/L ratio will be equal to n. The same applies there. So if these two devices would have been PMOS, then this should have been a pull-up network. In that case, my sizes would be 2p and 2p. But please understand one thing, that n is equal to 1.5 and p is equal to 3.75. You have to always remember this thing. Okay. So I can also have an equivalent of this thing, that two PMOS devices in series. Then the scenario would be like this. I have plus VDD. I have the first PMOS. I have the second PMOS, and here I have the output Y, and here we have the pull down network. So, and I know that my W by L equivalent should be equal to P, because if this circuit would have been a CMOS inverter, then I would be having a single PMOS device between output node and VDD, size was P. So just like before, only when I have the first PMOS with size 2P and second PMOS with size 2P, then as per equation number 3, my W by L equivalent would now be equal to 1 over 2P plus 1 over 2P equal to P, that is equal to CMOS. Okay. It's very clear. Now, last but not the least, the discussion, what about when MOSFETs are connected in parallel? So while we have already derived in equation number 4, what is the equivalent W by L ratio when MOSFETs are connected in parallel? Let us take a practical scenario here, and we will see which rule we must apply. So I will say now here, consider three PMOS devices connected in parallel. Okay. First PMOS, second PMOS, third PMOS, all of them connected in parallel, and here I have my output node Y. Okay, now listen carefully here. There are three possible paths between Y and VDD. So I know that I have to connect this point here. So I have three paths. The first path is this. And this is path number 1. 1, path number 2, and I have the third path. Okay, path number 3. And as we told here, what is the definition of pull strength? The pull up strength of each path between Y and VDD must be P, and the pull down strength of each path between Y and VSS should be equal to N. It's very simple that there are three ways in which I can connect. There are three ways in which I can connect my output node Y to VDD, and every path should have the pull up strength as P. So naturally, if I want to connect Y to VDD through path number 1, my size of the first PMOS should be P. If I want to connect Y to VDD through the second path, equal to P. If I want to connect Y to VDD using path number 3, P. It's very, very simple. This can also be applied to pull down network in the same way as before. Here I am output Y, and here I have three NMOSs in parallel. 1, 2, and I have 3 connected in parallel. Okay, same like before. I have three paths between Y and VSS. Okay, I'll make it reverse way because pull down. So path number 1, path number 2, path number 3. All three paths should have the pull down strength as N. So N, N, and N. Okay, it's very, very simple. So using these conclusions, we are in a position to now start to learn how to calculate the on-chip area of a CMOS system. Okay, it's very simple. So first we'll calculate the on-chip area of a 2-input NAND gate. Okay, just see how am I calculating it. Calculate the on-chip area of CMOS 2-input NAND gate. And understand one thing, that you cannot calculate the on-chip area of a CMOS layout without using the sizing rules discussed till now. Okay, once you are very, very clear about what are the individual W/L ratios of MOSFETs when connected in series and parallel, so that the effective pull-up strength of the entire pull-up network is equal to P, and the effective pull-down strength of the pull-down network is equal to N. Once you are clear with this, very, very simple. Okay, so the first thing which you have to do is you have to draw the transistor level layout. Okay, so okay, transistor level schematic of CMOS 2-input NAND gate. Pull-up network P1 parallel P2, pull-down network Okay. See now, first we'll find the sizes of P1 and P2. So first let us name them. Okay. So this is P1, this is P2, this is N1, and this is N2. Now pull-up strengths. So it's very clear now we discussed that the size of P1 should be equal to P and the size of P2 also should be equal to P, so that whichever path we take from output to VDD, the pull-up strength available is P. And as usual, NMOSs are connected in series. So in order to have the effective W by L ratio of the pull down network equal to N, the individual sizes of the NMOS should be 2N and 2N. It's very simple now. See, so now what we do is we write P, okay, better write N first. So we have N equal to 1.5 and we have P equal to 2.5 times N equal to 3.75. These are the preliminary calculations which you must write here, and I will show you where to use these values. Okay, now we go down and write that because N is 1.5, that means the value of 2N is equal to 3. Is equal to 3. That means what? The size of individual NMOSs are 2N, but the value of the size is 3. Okay, see now. So we make a table like this, which makes things very easy. So first I will write down the device. Okay, so we have 4 devices. P1, P2, N1, and N2. So first we write down the device names. Then the second column I write is the size. The size of P1 according to this is P. The size of P1 is P. Size of P2 is P. Size of N1 is 2N. Size of N2 is also 2N. Now we will write down another column called as size value. Okay. So size value means we are replacing P with 3.75 and N with 1.5. Okay. So because it is P, the size value is 3.75, 3.75, and 2N will be equal to 3, 3 and 3. Size value is 3.75, 3.75, 3 and 3. Now after the size values are obtained, now what is the purpose? On chip area. The third important formula which we need to remember is that the area is equal to width into length. So the width of MOSFET into length of MOSFET is the area of MOSFET. Okay. So here we will write down some more columns. Width of PMOS, length of PMOS, width of NMOS, length of NMOS, area of PMOS, area of NMOS, and the summation of the areas of all 4 MOSFETs is called as on-chip area. Okay. So now another important rule which we know is that if suppose I am having a technology equal to 100 nanometers. Okay. So we know another rule that the length of PMOS is equal to length of NMOS is equal to target technology. The third rule which we have to remember here. Okay. So I am assuming here that this numerical has to be solved. So calculate the on-chip area of CMOS to input NAND gate for 100 nanometer process. Okay. This is given in numerical. So I know that because the process is 100 nanometers, that is why my L is equal to 100 nanometers. Very simple. So we already written that LP is equal to Ln equal to 100 nanometers. So I can write down here all values. So all these values are in nanometers. Okay. So LP is 100. Ln is also 100. Okay. So What is important is to find out the widths of PMOS and NMOS. Okay, now very important here, you will get confused here. So the size of P1 is equal to 3.75. What is the width? So it's very simple, we can write it like this, that size of MOSFET is equal to W upon L. Okay, therefore we have P is equal to width of PMOS upon length of PMOS. Similarly, the size of NMOS is equal to width of NMOS upon length of NMOS. Okay, so for P1, if we consider the MOSFET P1, the size value is 3.75. So for P1, we have size equal to 3.75 equal to WP upon LP, which is equal to WP upon 100 nanometers. That is why the width of the first device WP comes out to be 375 nanometers. Okay, so we can write down here 375 and again 375. Now we have to calculate for the NMOS devices. So for N1, so we can say for P1 comma P2 and N1 comma N2, size is now equal to 3, size value, which is equal to Wn upon Ln, equal to Wn upon 100 nanometers. Therefore the width of NMOS devices is equal to 300 nanometers. Okay, so we put this derivations here, 300 and 300. So we can calculate the individual areas now. They are big numbers, so we will give more space. So area of PMOS, area of NMOS. So for P1 and P2, the area of NMOS will be dash, and for N1 and N2, area of PMOS will be dash. Very simple now. So it is nothing but 375 37500 37500. We have 3000. Okay, so the area of pull-up network is nothing but, so we can write it like this, area of NAND gate is equal to area of pull-up network plus area of pull-down network, which is nothing but area of P1 plus area of P2 plus area of N1 plus area of N2. Okay, so I think so it is very easy. So it is 375 into 2 plus 300 into 2. So we have 375 00 into 2. It is 75,000 is nanometer square plus 61234 nanometer square. Total area comes out to be how much? It will be 75,000 plus 60,000, 135 135,000 equal to 135. Okay, so conclusion is this. Now if you want to calculate the area of NOR, so using the previous rules, this is 2p, 2p, n and n. Okay, and again we are assuming for 100 nanometer process. So we have 2p equal to 2 into 3.75 is equal to 7.5. And here n is equal to 1.5. Okay, so like before, we have devices P1, P2, N1, N2. Size 2p, 2p, n and n. Size value 7.5, 7.5, 1.5, 1.5. Okay, WP, LP, WN, LN, AP, AN. Okay, as usual 100, so nanometers. Okay, So for P1 comma P2, size is 7.5 is equal to WP by LP is equal to WP upon 100 nanometers, which gives us is equal to 750 nanometers. So we have 750 here. Similarly, for N1 comma N2, size equal to 1.5 Wn by Ln, Wn by 100 nanometers. So we have Wn is 150 nanometers. Okay, so area of NOR gate is equal to 2 into 75000 plus 2 into 15000. So 75,000 into 2, 150,000. Okay, so now we are in a stage of comparing the area occupied on chip. Okay, so area of 2 input NAND gate is 135,000 nanometer square, and area of NOR gate is 180,000 nanometer square. So percentage area saving is 180,000 minus 135,000 upon reference is NAND gate. So 135,000 into 100. So 180 minus 135 upon 135. 180 minus 135. 33.33%. That is why we said that a VLSI engineer will always prefer a NAND gate over NOR gate because it occupies 33.33% less area. Now, if you have understood how we calculated the on-chip area for NAND and NOR, and then we also compared as a practice and as an exercise, you can actually take it as a home assignment that what will be the percentage area saving between 3 input NAND and 3 input NOR gate. Okay, so that is why we say here say since 2 input NAND gate occupies 33.33% lesser area on silicon wafer than 2 input NOR gate. For fabrication purposes. Okay.